Hi, thanks for listening to my talk. My name is Daniel Mogimi and I'm a PhD student at Worcester Polytechnic Institute. Today I'm going to talk about my work on side channel attacks on trusted platform modules. In TPM-Fail, we found timing vulnerabilities that expose cryptographic keys from trusted platform modules. This is a joint work with Berg Sunar, Thomas Eisenbart, and Nadia Henninger. Let's motivate this talk by looking over a simple cryptanalysis example on ECDSA signature generation. Let's say we have a crypto system that has a key K and an input and output. The job of the crypto analyst here is to recover this key by just looking at the input and output of this crypto system. If the crypto system is implemented securely, this should not be possible, and the attacker doesn't have any luck to recover the private key by just looking at the input and output. But about 10 years ago, there was this news about the big BS3 hack. So what happened here is that in ECDSA, as we see the equation on the left side, there are two secrets during the ECDSA signature generation. One is the private key D, and the other one is the nonce KI, which the nonce should be generated randomly and unique for every single message. However, at the time, somebody at Sony decided that it's a good idea to use the same nonce for all the generated signatures. And what happened here is that by substituting two of these generated signatures, we get a simple equation with one unknown, and we can just calculate the private key from this resulted from this known signature values. So this example shows how important it is to keep these nonces private and also unique per signature. So in this work, in addition to the input and output of this crypto system, we also assume that we have access to an additional signal that is leaked through a side channel. And there are so many different type of side channels out there. There are some attacks that need some physical access, like power attacks and EM attacks, but there are also some side channel attacks that can be conducted remotely, like the timing attacks or some CPU side channel attacks. And as we see later, these side channels really make the job of implementing these crypto algorithms really hard on a computer. So we mentioned that this work is about side channel attacks on TPMs, and these TPMs are just some security chips that are connected to our computer. You can find them on your laptop, on your desktop computer, or on any workstation, or even on your mobile phone. And TPMs are supposed to be tamper resistant and side channel resistant, which means you should not be able to steal crypto keys from these devices using side channel attacks or fault attacks. And we use these TPMs because we cannot really rely on the software stack, including the operating system and hypervisor in the cloud, to protect important credentials. As a result, we put important security keys inside the TPM chip and assume everything outside of this is untrusted. So even if the entire CPU core or the operating system is compromised, uh, we know that the TPM provide a better security guarantee for these credentials that we stored inside this. So to make sure we don't leave these credentials outside of this TPM chip, we also need to support cryptographic functionalities inside this microprocessor. And as defined by the Trusted Computing Group, TPM support a variety of standard crypto functions for hashing, encryption, or random number generation. But more importantly, they also support digital signatures based on public key crypto schemes. So why do we care about digital signatures in the context of this TPM technology? Well, these digital signatures are used almost everywhere on the internet for TLS communication or any sort of authentication. And thanks to the recent version of some software stacks like the OpenSSL cryptographic library or operating systems like Microsoft Windows 10, now we can compute these signatures on the TPM device instead of the host CPU. And as a result, the private key is kept more securely inside this kind of hardware-based vault. Another important use case of digital signatures for TPM is the remote attestation of the device itself. And with remote attestation, we can verify if a remote party is using proper system configuration and if it's a legitimate TPM hardware that we are talking to. with TPM version 2, which has been around since 2010. Now TPM standard is supporting digital signatures based on elliptic curves, including ECDSA, ECSHNOR, and ECDAA. We talked about TPM supporting standard crypto functionalities, but Trusted Computing Group, who came up with these standards, also expects manufacturers to have some security guarantees for implementing these security chips. According to their website, they expect vendors to demonstrate successful common criteria certification at level EAL4 plus moderate. And here we can see a list of devices that have the proper certification on their website. And for example, one of these devices that we tested in our work here is mentioned in that list. And we looked it up and we could find the data sheet for this ST microelectronic TPM and also the CC evaluation document that mentions some claim about sidechain resistance. Let's look at this data sheet. Let's look at this certification. They clearly claim that the device have countermeasure against sidechain attacks. For example, here in the certification, we see that there are different information. First of all, it says that the CDSA is also used for generating the endorsement key for this device. It can be a long-term key. The device supposed to protect against some assets and so on. And here there is a definition of what is considered a secret, the user key, or the any key generated is supposed to be a asset here. And here also it clearly mentioned that the device is supposed to have mitigation against SPA attack, timing attack, DP attack. And there are also some other parameters here that mention resistance against physical attacks like physical probing or fault attacks. So we clearly see that this TPM device, one of these devices have a certification. Now the question is, are these TPM devices actually secure against sidechain attacks? One of the interesting class of sidechain attacks is the timing attack, as it is not intrusive, it can be done remotely, and we don't need a special equipment to do this attack. And for proper timing analysis of these TPMs, we figured out it's a good idea to use the CPU cycle count as a timing resource. And why is that the case? Well, the TPM that's connected to our system generally is based on some microcontroller that runs maybe 100 times slower than the CPU. So the CPU cycle count here can serve as a high resolution timing resource with almost nanosecond resolution. Initially, I did some tests on a TPM technology called Intel Platform Trust Technology, and this Intel PTT or Platform Trust Technology is basically a firmware-based TPM that runs as part of the Intel Management Engine. Intel Management Engine has its own microprocessors, but it's on the same die, and this has become very popular on modern consumer computers because the manufacturers don't need to attach a separate TPM device to the motherboard. And at the same time, the TPM operation is still separated from the CPU cores that runs the operating system. And here we can see the result of some timing analysis of ECDSA operation on this TPM device. And as we can see, this histogram suggests that the ECDSA is not actually constant time. And as we can see, some of the signatures on the left side of this histogram are generated faster. This motivated us to build a tool to do this measurement even more precisely. So we implemented a kernel module that modifies the behavior of TPM kernel stack on Linux and performs this timing measurement as close as possible to the MMIO interface that is connected to this TPM device. And with this tool, we realized that this timing samples actually has a has kind of a symmetric behavior where we have different timing brackets in our histogram, and each of these brackets has 4 times more number of samples compared to the next one. we looked more closely to see what is happening here. Why do we see this very organized timing behavior? And we realized that there is a relationship between the nonce and this timing behavior. Here, if we look at the ECDSA equation again, we can see that with the knowledge of private key, we can of course recover the nonce and analyze it. So we programmed the device with a known key and recovered the nonce for each of these signatures that we generated. And we realize that for every additional 4 bit of 0 in the most significant bit of the nonce, we have some order of magnitude faster signature generation. And for more number of zeros, we also get a very high timing difference. For instance, for 12 bit of 0, you can see that signature generation is more than 3 milliseconds faster. And as it is listed here, all of the elliptic curve schemes that were available on this Intel FTPM were vulnerable to this attack, but some of them have different magnitudes, and you can find more detail about this in the paper. So let's see this attack in action. Here we have a script that we prepared. That this script basically generates a new ECDSA private key, and then it programmed the TPM device with this private key and do a signing operation to sanity check everything is working. And as you can see, we generate a new private key and we program the device with this private key. So here is the private key. This is the private key that the TPM device is programmed to work with. And then we have another script that basically sign a new message and also uses that TPM TTL, which is a client application that uses our kernel module to measure the timing of the operation. So if we use this, we see that we generated a signature pair, some signature information, and also some timing information regarding that. So we run these scripts that basically generate signatures, and at the same time, we have another script that plot the live histogram of the new signatures that we generate. And as we can see, the histogram starts to shape the look of what we just described before. And here, as we generate more signatures, we see that, for instance, the ones in the middle they have 4 bit of 0 bits at the most significant bit, and so on. So this is the leakage on the Intel FTPM, but we also looked at some other TPMs that were attached to our computers in the lab, like different laptops, different desktop computers. And during our analysis, we found that many different operations like ECDSA and RSA operation are not constant time on these devices. But one of these devices, which is the TPM from ST Microelectronics, is also vulnerable to a similar leakage for a CDSA. So here we can see the timing histogram for ECDSA operations on the ST Microelectronics TPM. And we can see that the Gaussian distribution here is not fully uniform, even though it does not have an obvious pattern like the other one. So we similarly looked at the nonce for the signature generated by this device and realized that there is a similar vulnerability here, but instead of for every 4 bit of 4 bits seeing a different timing, we see a different timing for every additional bit of 0 bit at the most significant bits of the nonce, which may suggest that the developers have implemented some sort of algorithm that processes the nonce bit by bit and it leaks the bit length of the nonce. The plot here on the left side shows that there is a linear correlation between the bit length of the nonce and the timing operation. So So far, we just have some partial information about the bit length of the nonce. This is not as powerful as the naive case of Sony using the same nonce for multiple signature. But what can we do with this? And there is an answer to this. We can use lattice attack to basically recover the key from this. So we systematically perform an attack which starts with collecting signatures from the TPM device that is programmed with some unknown private ECDSA key. Then we filter the signatures that we generated uh, based on a known bias. And we know this bias because we filter the signatures based on a template that we generated uh, during the discovery of this vulnerability. And after filtering the signatures, then we feed the signatures that have a bias to a lattice-based key recovery algorithm to recover the long-term private key from the TPM. How does the lattice-based attack work? Uh, Not going to get to the detail, but the main idea is that if we rewrite the equation to a simpler form here, in this simpler form, we have some known value that is labeled as A and B with the green color, and the secret values are red, the nonce, which is KI, and the private key. Obviously, without the side channel information, we cannot simply calculate one from the other because we have one equation and it has two unknowns. But thanks to the side channel information, we have an additional uh, signal here that tells us that the nonce cannot be bigger than a specific size. This problem is known as the hidden number problem, and there is a techniques based on lattices that can recover the private key from these nonces in polynomial time. And these lattices have been studied for a long time, of course, by mathematicians and the crypto community, and people also have used them to recover ECDSA key from nonces that are generated with a bad random number generator, for instance. So we constructed our lattice exactly like this matrix here that we see in this slide, and when we fit this construction with the filtered signature to an algorithm called LLL, this magically recovers the private key for us, and generally you can compute this on a laptop computer in less than a couple of minutes. So here again, we see another demo that shows this in practice. Again, we looked at the data, the results that we generated uh, previously, and we have, for instance, thousands of signatures. And when we plot this, we see that at some point, these signatures are faster or slower. So we know what is the threshold that some of these signatures are generated with a known bias. So we are interested on the short signature. So we modify this script here and put a threshold that matches the signatures, and then we filter the signatures that are generated short. And we have 99 signatures in this case that are basically have 8 bits of most significant 0 bits, and then we can basically use another a script here we have that uses the sage math to recover the private key from these signatures. And here we hard coded the private key here to do sanity check, but the idea is that uh, we solve this equation using the lattice technique, and then we have a small number of candidates, and we go through the candidates, and one of them is the key. And we can see here that in a couple of seconds, we can just recover the key in all cases successfully. So this was the attack, and we did some thorough analysis of this attack with different number of signatures and parameters for our lattice. And here we can see some of those results. We tried with different lattice dimensions and different number of signatures, and the end result is that on the FTPM case, we can recover the private key with only 1200 signatures, which takes maybe 3 to 4 minutes to collect these signatures. And for the SD microelectronic case, also we can efficiently recover the private key. We just tried with the most reliable setup in our case, which was using really short nonces, and the private key, we could recover it with like 40,000 signatures, and that can be collected in like 80 minutes. So we saw that we can steal this private ECDSA key from this TPM, even if they are certified or they claim that they are secure against these attacks. And these TPM devices, also their threat model also should uh, actually stop against these attacks, even against physical attacks. But now we even go further and we talk about network timing attacks and attacking these TPM devices over the network. So these remote timing attacks were previously proposed to attack against RSA or ECDSA, and mostly in lab setup. And we can here ask the same question: can we do these remote timing attacks on TPM devices? So we looked at closer to the timing difference of different brackets in the Intel FTPM case, and we see that there is a more than a, if we calculate based on the CPU frequency and the timing distribution we got, we see that there is like about more than a millisecond time difference here for each bracket. So in my local network, I tested like a couple of days ago, I can ping another computer in less than a millisecond. And this tells me that uh, seeing like multiple milliseconds in a network that is being less than a millisecond round trip time is probably observable. And even network attacks on internet, it may be also possible, because on some fast networks, for instance, here in this case, if I ping the Cloudflare DNS, I may get a round trip of about 20 milliseconds. So seeing maybe 3 milliseconds of difference, it could be possible. Well, in our paper, we only demonstrated the attack on a local network, on a real application for VPN connection. So we configured a StrongSwan VPN to use a TPM device. And according to their documented instructions on their website, uh, if we configure StrongSwan this way to use TPM for authentication, the IKE protocol first does its normal operation of TPM key exchange with the server to have a shared secret for encryption of the VPN communication. But after this first handshake, the server here asks the TPM to sign a message and return the signature to the client. So the client here knows that it's talking to a legitimate VPN server if the server sign this message with a proper key, and we know that the server is not impersonated by some man-in-the-middle attacker, which means if somebody steals this key, they can impersonate this server. So the next thing that happens is that in the second handshake, the client, which is malicious here, can just measure the time of the second handshake and just drop the second connection and repeat the handshake again. And with repeating this handshake, this malicious client will have enough signature pairs and timing information to conduct the attack that we described before. So again, with this information, we can perform the same attack, and but this attack is of course has some noise due to the network timing. And in our experiment, we could recover the private key with about 60 to 70% success rate with lattice dimension of 90. And this lattice dimension, of course, is related to the number of signatures. And here uh, in our case study, basically, we needed about 44,000 handshakes to have enough signatures that give us this information to recover the key, which took about 5 hours to conduct this attack. So just a recap of our results. We also analyze this in more depth in the paper. The attack is successful for so many different scenarios, including root access all the way to remote access over the network. And it's just that we have to deal with different amount of noise and different trade-off of uh, sampling and different way of putting the threshold to find proper to find signatures that have a bias that we need. So now the question is why do we still have these problems? And this is not the first time that we find such timing vulnerabilities on some of the Intel products or other crypto library developers. In like about like 2 years ago, 3 years ago, we also attacked a scheme that used some elliptic curves called EPID, and this EPID also basically was vulnerable to a similar attack that we could find the bit length of the nonce. So at the time, this kind of got us more curious. We to understand what's going on here. So the actual problem here is that implementing crypto is not easy. Even if the math, if the theory is secure, there are so many ways to implement a crypto algorithm. Here again, we see the ECDSA equation, and ECDSA there is two simple operation on the curve. There is a double operation, which by doing this double operation, we get another point on the curve, and then there is the add operation, which we do a similar thing with 2 points on the curve. So you can implement, for instance, a scalar multiplication operation using just this add and double operation. And here, for instance, we can see that for different value of a scalar, multiplying this number to this point needs different number of add and double operation. So this just translates simply to an algorithm called add and double to calculate the scalar multiplication operation. And when we generate a ECDSA signature, we have to do this scalar multiplication each time. But this is not as simple because this add and double algorithm is not the most efficient algorithm, and it's also vulnerable to so many different type of side channel attacks. So people have come up with so many different type of algorithms to just do the same operation, including uh, like a sliding window algorithm and fixed window algorithm. And our guess, also based on our observation of other codes developed by Intel IPP, we guess that this implementation that was vulnerable for Intel FTP was a fixed window implementation with window size of 4-bit. But the challenge here, as we see for software developers and crypto developers, is that it's not clear what side channel means, what is the threat model. So people generally implement a crypto library that they may deploy it in an airplane or on a cloud computer, and that's kind of difficult. So we wanted to basically have a tool like about 2 years ago we implemented this technique before even we found this vulnerability on TPM devices to find these leakages in the software by have some model of the leakage. So how did we model this? The idea is that we, for instance, in the software, we have some secret dependent control flow, or we have some secret dependent memory accesses, like in SBox operation in some block ciphers, or on some CPUs or some microcontrollers, like for instance on some ARM CPUs, we have some operations that are not constant time. So we want to actually look in the software and see if we are doing any of that depending on the secret key. And if we find that, we can report that, oh, this is a leakage behavior. And we wanted this approach to be automatic, so we basically applied some dynamic analysis approach, and also we wanted a tool that does this operation in a binary level, so we can analyze crypto libraries that are closed source. So the high level idea of how is that we proposed a tool and we implemented this tool called MicroWalk. And the model is that in practice, attackers measure things like execution time of a loop or the memory access pattern of those SBox operation. But in theory, attackers get access to some sort of execution trace with, for instance, the number of executed instructions or the branch that have been happened or the target of the branches or the offset of different memory accesses. So that's what the attacker wants to learn in theory, but the attacks are not perfect. So the attacker just learns some noisy information. But we as a defender or we as an observer, we can actually model this behavior and focus on the software here. So in MicroWalk, our approach is that we generate a set of random test cases and capture the execution trace. We have two ways of then analyzing this execution trace. One is based on just computing the pairwise difference of these two traces that we generated. And we have a second approach that we use some metric here in this paper. We use the mutual information between the execution traces and the input to see if any of these instructions that are executed during the computation has a score that is more than one, and if there is a score, it means that that information contributed to some amount of leakage. To collect these traces, we use dynamic binary instrumentation, and we use the Intel pin tool in our case. So the first phase of our attack is that we collect these traces with pin tool, and after collecting these traces, we also sometimes apply some tweaks to the trace by, for instance, emulating the CPU or replacing the random numbers to have more control over the input that is fed to this software implementation. So after that, we also do some pre-processing of the trace to normalize the trace because, for instance, things like memory accesses may just differ from one execution to the other, for instance, because of the memory allocations or the randomizations that exist in the page level layout. So we remove all of these and we make the trace more compressed and also more normalized. And then in the last phase of the analysis, we feed this normalized trace to our analysis system, which uses one of the two techniques. So this MicroWalk tool, we actually had this before we found this TPM vulnerability, and we believe that this tool could actually help these manufacturers to find these vulnerabilities before we find them on the actual consumer products. So the story of the coordinated disclosure with these vendors is that with ST Microelectronics, we reported these vulnerabilities to them like in 2019, in May 2019. They acknowledged the receipt. We had lots of phone calls with them to walk them through the process of coordinated disclosure. And at some point also, we helped them to verify that the new version of their TPM firmware is not vulnerable to this device anymore. And later on, some computer manufacturers like HP and Lenovo, they issued firmware updates. And for Intel, it was a longer process. We reported this vulnerability to IPcert in February 2019. They acknowledged the receipt, and they also confirmed that the reason this vulnerability happened was because they were using an outdated version of the Intel IPP crypto library. But the process was straightforward. They did the firmware update after the embargo was done. And here also, I want to mention the results from the MicroWalk tool. So in 2018, we reported some vulnerabilities in Intel IPP crypto library as a result of our analysis using the MicroWalk tool. And we see that these vulnerabilities, again, happen again and again. For instance, these CVs, some of them are actually related to the similar problems in their crypto library, which we can see here the timeline is before the TPM case. So I would be happy to take a question, and here are some links to the website that is dedicated to this attack and the tool. And if anybody is interested to read more about it or contact me about the tool, I would be happy to take questions. Thank you.